Hi everyone, thanks for coming. So my name is Patrick, and the title of the talk is Controlling the Go Runtime. So there are two main things that I'd like to talk about today. The first is, how can we control the Go runtime? What methods, what functions, what ways are there built in for us to control it? The second thing is to answer the question, why is that so good? Why is it a good thing to control the runtime? So we're going to talk about that too. So here's the plan. Straightforwardly, we'll talk a little bit about what the runtime is, ways to control it, and perhaps a little surprisingly, I'll talk about some experimental ways to control it. So let's get started. So reminder, probably for many of you, but just so we're on the same page, what is the Go runtime? I think we could think of it as a library used by Go programs while executing. And what sort of library is it? Well, have a look in the runtime package in the standard library. It's that stuff in there. That's the sort of stuff that I want to talk about. That's what the Go runtime is. There are two main parts to it. There's the sort of the garbage collector, the part of the runtime that manages memory for you. And there's the Go routine scheduler that decides when and where and how those snazzy little Go routines will run. Just to fix a metaphor, I think it's convenient to think of the runtime as kind of like a helpful assistant. So if you have a Go program, here's a simple one, or at least a part of one, and you compile it into a binary, and then it starts executing. While it's executing, at certain points, it will call out to the scheduler and do some things. It'll free memory, it'll schedule a different Go routine, things like that. And all that is happening inside the runtime library. Importantly, this is a Go conference. Sometimes other sorts of environments use the word runtime. That's a kind of different world. Interpreters, JVMs, things like that. That's not what we're talking about here. The Go runtime is not like, say, a JVM, which executes some kind of intermediate form or perhaps even has some just-in-time compilation. That's not the sort of thing we're talking about today. All right, so what on earth is in that package? Well, a multicolored display of stuff. You don't need to read all this because we're not going to talk about all of it, because most of it is concerned with things like profiling and observing what's happening with a running Go program. So for instance, there's a function there that tells you how many Go routines are alive at the moment. Or there's another function to turn on tracing. So we're not going to talk about those things today. What I'm interested in talking about today are ways that we can directly control the runtime using some of these library functions. And in particular, these 8 functions here, about half of them concerned with the garbage collector, and about half of them concerned with the scheduler. So let's dive in a little bit deeper and have a look at what those functions do and how they work. So first, these for the ones for the garbage collector. So there's one called GC, and that says, stop everything, collect all the garbage. It's a blocking call. It runs the garbage collector immediately. There's also a function called keep alive. What that does is it says, don't collect, don't throw object away yet. We're going to need that at least until now. Be sure to keep that around. And then there's another function called setFinalizar that sets up a function f that can be called when that object is ready to be garbage collected. I should ask, by the way, has anybody used any of these functions before? Can you raise your hand if you've used them? A few people, enough that you can see that some people have used them, but not everybody. What about those ones to control the scheduler? Well, there's one GoMax procs. What does that do? That's sort of the analog of the GoMax procs environment variable you've probably heard of. What that does, what this function does, is while the program is running, it can change the number of maximum simultaneously executing processors are available. Go exit immediately terminates the call and go routine. Ghostcat yields the processor now, and it lets some other go routines run. And then there's the somewhat mysterious lock OS thread, which connects a running go routine to the current OS thread. What does that do? That ensures that that go routine will always run on that thread. Anybody use lock OS thread? Not too many, a few. Well, let's see why, if anybody's actually using this thing. So I took a look. I thought, well, maybe these are kind of arcane things nobody cares about. Nobody ever used them. And what I discovered is that's not true. People are using them. So if you have a look here, so what I did is I looked at the BigQuery public data set from GitHub, and I did a search, not a very scientific search, but a quick search to just get a sense if anybody's using these things and how they're using them. And I found, say, an interesting thing, that runtime GoMax procs is in fact even used more often than HTTP listen and serve, which probably, how many people have used HTTP listen and serve? Most of you. But yeah, maybe 1/10 of the time that func main occurs there in the public data set, the main entry point for a Go program. But just to keep things in perspective, they're not used that often, so time now, format error F, those things are used far more often than this. Unsafe pointer is used often. I know if people are being risky, maybe somebody should do a bit more investigation here to understand why. So apart from those functions I just introduced, there's some other controls here I'll just mention and not talk about, but just so you know they exist. In the debug package, there's some other things like setting the maximum number of threads and so forth. And there are those environment variables, GoMax procs, you've probably heard of, but just as a reminder, what that does is it sets the maximum number of available processors on startup. And there's GoGC, which gives some control over the garbage collector. In fact, you can turn the garbage collector off if you like, using that environment variable. Now, those ways we just talked about are ways we can directly control the runtime. But I think it's worth pointing out that the context, in a sense, say the cancel aspect of context, is another way, perhaps just an indirect way, that people are using to control the runtime. So when you call context with cancel, what that does, how many people have ever used context before? Let's try that. Yes. So context is everywhere, especially if you work for Google. It's required that you add context as an argument, apparently, in the functions you make if you work at Google, just so you could manage the kinds of things that need to be managed. So anyway, what does cancel do? So when you create a context with cancel, it returns this function cancel that lets you request that all the Go routines that have that context stop. What's that doing? If you think about what it's doing, in effect, it's an indirect way of saying, let's stop all this group of Go routines. So it's a way of controlling what the scheduler is doing. It's saying, turn off all these Go routines, in effect. bit more precisely, it's requesting that they stop. Maybe if you're not listening to context, they won't stop, but it's expected that you will. So why on earth does anybody need to do this? We only saw a few hands go up when asked if anybody's using these functions. So we should ask, are they really important? We understand a bit better what they are, but do we really need these things? Why are they good? Now, when I started having a look at this, my interest was in the performance of Go programs. What I was interested in and what I was expecting to find is that there were some available ways that were going to help me make my program run faster. Everybody wants their program to run faster, and I thought, oh, well, maybe I can find some good ways to make my program go faster. That's what I was expecting to find. So let's see what we find. So let's go back to these functions that are used to control the scheduler and see how they're actually used. So how about GoMaxProx? Why would anybody need that? So I don't know if anybody's used the handy CPU flag in GoTest, but what that does is that runs the tests several times with different settings for GoMaxProx. So here in this example where it says minus CPU 124, it runs the test 3 times, once with 1 available processor, 1 with 2, and once with 4 available processors. And if you have a look in the testing library, conveniently enough, there it is, calling runtime GoMaxProx. That's how it works. It seems quite useful. Another place you see this function being used is to respond to the situation in which a running container changes the amount, a running container modifies the available resources to it. So for instance, suppose a running container has 6 CPUs available to it, but the system doesn't want it to use so many resources, so it reduces the number of CPUs available to that container, say down from 6 to 4. But there's a Go program running in that container, and the Go program, you don't want that to think there's 6 available CPUs. You want that to match what's just happened to the container. So people use GoMaxProx to do just that. When the resources change on the container, the running program can match what happens to the container. You can see that in an example in the Jaeger tracing library, uses something from Uber that does that very thing. Interestingly, in the code, this is in the code in the standard library, it says, this call will go away when the scheduler improves. It hasn't gone away yet, and even more so, there's a GitHub issue where someone's saying, make that go away. The scheduler's better now. We fixed it. It's good enough. Get rid of this horrible GoMaxProx thing. And the issue was closed and rejected with someone saying, oh, we can't get rid of that yet. It's too useful. GoExit. I doubt anybody's ever used, or very few of you have used GoExit directly, but it turns out you use it all the time. Anybody who writes a test and you have a call to tfatal here in the test, what's happening internally is using GoExit, because what happens internally is that tfatal calls another function, I think it's called, or a method called tfailNow, and failNow calls GoExit. And if you start thinking about it, you might realize, or at least it appears to me, very difficult to imagine how you could write a testing library that has a function like fatal that's gonna, say, run each test in a separate Go routine and have that test somehow end. How can you do it if you didn't have anything like GoExit available? Ghostcat. So remember what that does. What that does is it yields the processor to some other Go routine. Which Go routine? Well, we don't know. Let the scheduler decide, but anyway, we're not going to run anymore. Why would you need that? So here's an example. This is in a test, but basically, I think similar cases can be found elsewhere. The idea is, suppose you have a CPU-bound kind of algorithm, but you don't want it to hog the CPU. You want at some points to just let go and let something else do something. So if we're in this test, it's important to let something else do something because it wants to test a certain case. So what's it do? Every 1,000 steps, it runs Ghostcat to ensure that other things run. And it doesn't do this tight loop without other things running. All right, lock OS thread, the mysterious lock OS thread. Remember what that does. What that does is it says, look, this Go routine needs to run on a particular thread. It really can't run on some other thread. It turns out there are a couple reasons why that's important. One of them is that certain libraries, like Coco and OpenGL and so forth, use thread local state. So if you call things in that library, you need to ensure that when you call again, the state is there. It can't be that your Go routine started running on some other thread and somehow you lost the state. So that's one place you see this function used. Interestingly, in the documentation, it says this: Go provides the runtime lock.os thread function for this, but it's notoriously difficult to use correctly. And I just want to pause here and just think about this comment, because I think there are two aspects to this that are really, I think, good to focus on. The first is, in the documentation, it's clear that this function, although perhaps only rarely used, is very important. It really needs to be used sometimes. And the second aspect of this is somehow the thought that this is a bit mysterious and strange, and better not use this if you don't have to, better left to the experts, something like that. There's some kind of thought there. You can see it. Here's another example where it's used in signal handling. In the standard library, has to ensure that that Go routine is on the same thread, or else the signals aren't handled correctly. All right, so let's move on, talk a little bit more about the garbage collector and these functions here. So GC, remember that what that does, that starts garbage collection immediately. Why would you ever want to do that in a program? You think, do I want to slow it down? Why do I want to run garbage collection now? So here's why, and it's used in several different places in interesting ways. So think about this. So suppose I make a slice of integers. It's quite a large slice. And I compare that to what happens when I make a slice of pointers to ints. It turns out the garbage collector behaves quite differently. It doesn't perform as well when it's dealing with pointers, because what it has to do when it's dealing with pointers is different than what it has to do when it's doing things with mere slices of integers. But how could you find that out? How could you find out how the garbage collector is going to perform with your program? Enter GC. You write a test or a benchmark that runs GC, and you can find out how your program is performing. And you could change your program and see whether it performs better with regard to the garbage collector. Keep alive ensures that something is not garbage collected yet. It's being used in the net package in the standard library. So what's happening here? What's happening here is it's making a system call to set a socket option, and then immediately on the next line it says runtime keep alive. Well, why is that there? It wants to ensure that the file descriptor still exists while the system call is occurring. We don't want the system call to start or be blocked and waiting or something, and then the file descriptor suddenly gets garbage collected away out from under us. We need to have it still alive. Set Finalizar, if you've ever used CGO, Sometimes it's a good idea to ensure that the CGO objects you've created are freed up correctly when they're no longer used. You can see it in OS in the standard library. It sets a finalizer on the file descriptor for a file in order to ensure that that file is closed. Interesting quote from Russ Cox. It's true that set finalizer is misused and overused by external programmers. We can't do much about that. But for the occasional thing like OS file, it's invaluable. So I think this is similar to that kind of thought we saw before. We have something that's very important sometimes, but we want to kind of avoid using this. It's a bit strange. Maybe we should not tell people about it or something. All right, so here's what I found. I thought I was talking to work on performance, but what I discovered that all these things are often used for cases in which you're testing, or you're verifying your program's correctness, or you're debugging the program, or you're profiling the program. I can see many places where these functions are used in that sort of way. So it's not just about performance. So why should we control the Go runtime? Why is it a good thing? All the reasons I just gave, for performance, for testing, profiling, correctness, debugging, things like that. So that's the answer to the two questions that I said we'd discuss today. The first was how to control it. So I told you some ways, and you can go looking in the runtime package. It's in Go, it's right there, and you can see what's happening with that. And why is it a good thing? Well, we saw all those reasons just now. So we still have 24 minutes left, so I'm going to do some experiments. Imagine what would happen if we could do better. Couldn't we do better than these things? Aren't there other things we could think of to control the runtime well that would help us make better programs? I have some suggestions. So these are just ideas at the moment, just proposals. But I think something along these lines might prove very valuable. And I'm interested to hear what you have to think about that. So I call the first Ghostcat next, the second Go affinity, and the third Go cancel. And in fact, I guess if some of you have your laptops out, I'm hoping maybe if not by the end of the talk, sometime tomorrow you will have implemented these and we can see how well they actually work. So what do they do? Remember, what does Ghostcat do? Ghostcat yields the processor, allowing other Go routines to run. Okay. What's Ghostcat next going to do? Well, that's going to do something similar, except it's going to instruct the runtime. It's going to tell it, this is what you should run next. Don't decide for yourself. I'm telling you what you should run next. The way I put it here is that Ghostcat next yields the processor, allowing a Go routine of a certain color to run. We'll get to what a color is in a minute. The important thing here is just to say that what's happening is that, in effect, you're telling the runtime what to do. You're telling the scheduler that the next thing I want to run is this sort of thing. Don't just decide for yourself. Danger signs appear. It's somewhat controversial to think that we should be using Go routine IDs. I just want to say right now, when I talk about colors, I'm not talking about Go routine IDs. This is a different idea. We'll be clear why in a moment. But let's talk for a minute about Go routine IDs and understand a little bit why people think those are a bad idea, to help us understand why the idea I'm proposing is a good idea, or at least a different idea. So here's something from the Go routine documentation explaining why it's a bad idea to have Go routine IDs. That is, having Go routines named. The fundamental reason Go routines are anonymous is so that the full Go language is available when programming concurrent code. By contrast, the patterns that develop when threads and Go routines are named restrict what a library using them can do. So there are, I think, a couple interesting ideas here, but one of them, I think, harks back to some of the things we just talked about before. It's somehow going to be bad if they're Go routine IDs. People will write bad programs. They will develop libraries that are not going to work very well. So we shouldn't have things like that for that reason. All right, so what is a color of a Go routine? A color for a Go routine is the type of Go routine it is. It's not a name for a particular Go routine. Some people maybe have heard of a difference between a token and a type. A token is a particular thing. A type is a kind of thing. What I'm talking about here are kinds of Go routines, not names for Go routines. I think it'll help to do it with a picture. So here's a nice picture from an old talk by Rob Pike, a very nice talk about, I think it's called something like concurrency and parallelism. What's the difference? So what's happening here? We have a bunch of gophers working hard. What are they doing? So the gopher on the left is taking up some books from a big pile and putting them in a wheelbarrow. The next gopher is running the wheelbarrow over to the right-hand gopher. The right-hand gopher is throwing those books into an incinerator. I don't have any comments about this example. And then there's a last gopher bringing the empty wheelbarrow back. All very good. So this idea, anonymous gophers, they don't have names. They just do their jobs. Here are the kinds of jobs they do. But if you look a little closer, we've got to be sure how we understand how this picture is modeling how a Go program works. Your Go routine is not like an anonymous gopher. Your Go routine is a gopher with a job. It's one Go routine does the job of putting the books in the cart. A different Go routine has the job of dumping books into the incinerator. So in effect, our Go routines already have colors. They have types. Different Go routines have different jobs. So there's the purple gopher. He has one kind of job. And the green gopher, he's the one on the right, has a different kind of job. So if we think about what we have already, we already have colors for our Go routines because each Go routine is started as a function, a particular function. And if you run that several times, you'll create a bunch of Go routines with the same function. So we already have, I think, Go routine colors. We just didn't know it. All right, so what is Ghostcat next supposed to do? So suppose that the purple Go routine calls Ghostcat next blue. What happens then? What happens then is the scheduler will run one of the blue gophers. That's what will happen. And if the Go routine, purple Go routine, calls Ghostcat next green, it will run the green gopher next, not the blue gopher. Oh, quite simple. It should be mentioned, though, there's some optimization in the scheduler. So if the purple gopher is connected to the blue gopher by some kind of channel, that is, the gopher putting books in the cart is connected to the gopher pushing the wheelbarrow full of books, if they're connected by a channel, the scheduler has some optimizations built in to ensure that the blue will run next. So I think it was added around Go 1.5 or so to make sure we're not in a situation in which we're passing messages to different Go routines, but the one receiving the message is waiting a long time to run and so forth. We don't want that to happen, so the scheduler was improved to ensure that the message passing is quite efficient and the next Go routine will run quite quickly. But it doesn't do this. It doesn't make the green one go. Well, why would we ever want the green one to go next and not the blue one? Well, we can think of some cases. And in fact, the second thing I think would be really interesting. I mean, you have the problems that you need to solve. You know the sorts of algorithms that are interesting to you. And I think it'd be interesting to see if you have any algorithms that could benefit from this kind of idea. So to pursue our analogy a little bit, why would this be useful to have green go next instead of blue? Imagine that the incinerator takes a long time to start, and in fact, it goes out often. So you need to kick the green gopher, get it to work to make sure the fire's going very quickly to ensure that that fire is going. And then he'll be ready to put the books in when they come. So if green gets kicked next after purple, we can ensure that green gets going, and then blue can do its work whenever the scheduler wants to make blue go. All right, so now once we get our crayons out, my daughter's 11 now, so she's beyond crayons, but she has some fancy markers, and you want to color in different ways. You want to see what happens if you put the colors in different places. And when you start thinking that way, you realize that this idea of goroutines having color is one that can be used in another way. So suppose the group of 4 at the top are one color, blue in this case, and the ones at the bottom are another color, green. What benefit would that provide? So that's what I want to call Go Affinity. What is Go Affinity, and why is that something that would be good? So Go Affinity, given a group of colors, Go Affinity requires or suggests, I'm not sure yet, that all Go routines of these colors execute on the same CPU. So all these Go routines are going to happen in the same place. So the group at the top, the blue ones would all be working together on one CPU, and the green ones would all be working on some other CPU, perhaps. But anyway, it would be guaranteed that the blue ones would all be on one CPU together. The incinerator gopher would not be lost on some other CPU. Some reasons that's a good thing. So one of the main bottlenecks these days in the efficiency of programs is merely the time it takes to get stuff out of memory and to put it back in memory. So there are all sorts of optimizations, level 1, 2, caches, 3, I don't know how many there are now. Why are they there? That's because it takes a long time to get stuff out of main memory. So if you put memory next to the core, then you can get it faster, and your program will run faster. So why would it be good to have all the green gophers working together on one CPU? Think of the books as something you want to store in nearby cache. We'll be able to keep it there. The Go routine won't wander over to some other CPU and have to drag the books with it. The books will be right there in the cache. Similarly and relatedly, the NUMA architectures have some cores more closely connected to each other in a certain sense than others, and it takes longer to move stuff from cores that are in different NUMA groups than ones that are together. And a third sort of reason to think Go Affinity would be a good thing, we could think of as isolation. What is that? Well, sometimes, so suppose you have some kind of program that does a lot of math stuff. I don't know, it's some kind of AI, machine learning-like thing that's crunching a lot of numbers, and it works really hard. But you don't want that, we don't want that part of your program to interfere with some other part of your program, say that's answering a HTTP request. We'd like the math stuff to happen somewhere else than the other stuff. It could be that we guarantee with Go Infinity that all the math stuff is going to happen together, and let the other stuff, say, land where it may, but we'll ensure in that way that all the CPU-bound math stuff doesn't leak over to infect what's happening on other CPUs. We can think of that as isolation. Okay, go cancel. So I asked before, whether anybody's used context before. Can you give me a show of hands? Anybody, how many people think they really like context? Context is a really good thing. Okay, plenty of people raise their hands, but far fewer people raise their hands than the ones who raise their hands when I ask them how many people have used it. At least for me, I find that cancel is a little bit clunky, makes it a bit hard for programs to read. You have to sort of structure them in slightly funny ways to ensure that the context is passed around appropriately. It's a bit inconvenient. It does its job, and it's important, but it's a bit kind of ugly and inconvenient. Well, what if we had something better? So suppose you could cancel all the Go routines of a certain color. Well, that's what Go cancel is supposed to be. So you want to make all the blue gophers stop working, you say Go cancel blue, and all the blue gophers will stop. Or at least, alternatively, it's requested that all the blue gophers stop. Why would that be an improvement over using context? I think one reason it would be improvement is that you could have more flexibility in how you structure your program. You wouldn't have to have Go routines starting other Go routines, starting other Go routines, ensure the context gets passed to all of them. Independently, you could start various Go routines and you could control them. So the some Go routine here could control a group of Go routines and get them to stop at once without trying to manage the context passing through. So in a sense, it's a way to generalize what we wanted to do using cancelable context, but it provides more flexibility and freedom to have a similar function and do even more. And perhaps even if we think about it a little bit more, maybe we'd like something like a broadcast mechanism, send a message over a channel-like thing into all the Go routines of a certain color. But that's beyond the ideas that I've started talking about here. So let's stop for a second. So I've been giving some interesting, perhaps, ideas about things that we could do and perhaps you will do and show me in a couple days. But I think some of you, perhaps a lot, may be thinking, this is a terrible idea. Don't do this. Don't do this. We should never control the runtime directly. That's not a good thing to do. Why would you even want to think of new ways to do it? We shouldn't have even done it already. This is a bad idea. One reason somebody might think it's a bad idea is they could say, look, once you start doing stuff like that, and we saw this in some of those quotes I presented about why it's somewhat weird and dangerous to use lock OS thread, for instance. Controlling the runtime is bad programming. We're going to make a mess of our programs, and that's not a good thing if we start giving these more powerful tools to control the runtime. You're just talking about IDs under another name. IDs, colors, it's all the same. That's the same bad idea. We left that behind with Go 1.2, that bad idea. Let's move on. And somebody else might think, look, let's just make the runtime better. All well and good to kind of do some tricky things while a program is running, but what we really want is to make the program run faster. How should we make the program run faster? Well, we all work together and we make the runtime better. Let's not have these kind of crazy knobs. We should just work to make the runtime better. So I think some people may have had thoughts like that. So let me say a few things about why. I guess I could just add, in the documentation they say, the runtime scheduler is not as good as it needs to be. We agree, we can make it better. We can do that. All right, so what can we say in response to people who think things like that? to try to convince them that this is a good idea. Well, I hope I convinced you already that the first idea, that we should never control the runtime directly, is just not correct. All the ways I talked about earlier in the talk about testing, verifying correctness, debugging, performance, they're all important things that we need to do, and we really do need sometimes to tell the runtime what to do in order to do them. So it's just not the right place to start to think we should never control it directly. What about people think, look, okay, we need to do it sometimes, but let's do it at night when nobody's looking. Don't do it often. Don't tell us about it. All right? Generally, if you do that sort of thing, you're going to make bad programs, and we want to make good programs. I think that's a strong thought. I think that's worth pausing to think about. I think one of the things behind that thought is the idea that somehow the runtime is like working on changing it to improve the runtime is kind of like working on the kernel. I don't know, the operating system kernel is this mysterious thing. We'll get some smart hackers with their PhDs or whoever to figure out how to make the kernel go better. It's complicated. Get somebody with 50 years experience who understands all that stuff to do that. And we'll make this general purpose kernel, and that'll do smart things. And then we write our application programs making use of that work that others had made. I think people may be thinking something like that. But if they are, we should remember this isn't like the kernel. The Go runtime is not like the kernel. The Go runtime is in Go mostly. It's in user space. It's together with your program. You can easily change it, which is why I'm hoping you will do it in the next 5 minutes. So we should think of it as something we could work on. Think of something we can build on. Think of something we can easily do things, create things to control it. But I think there's a second thought behind the idea that controlling the runtime is a bad programming that we should talk about. I think we mentioned before when we talked about this idea of Go routine ideas being bad because people write bad programs if we give them IDs. Let me talk about that in this way. So suppose I'm worried that my children will do bad things. It seems like it's not good parenting to lock them in the house to ensure that they don't do some bad thing. They need to go out in the world. They need space to do things. They need the tools and the ability to do things. So even if people may and probably will write some bad programs, probably all of us who've written programs have written bad programs, that doesn't mean we shouldn't make tools to help us write very good, very efficient programs. We shouldn't be afraid of people writing bad programs because we provided them with some tools that could permit them to do so. The tools are permitting them also not just to possibly write bad programs, which they could have written already before they had the tools, they're permitting them to write more efficient, perhaps, programs or better programs. IDs for Go routines, bad idea. I hope I convinced you not only that this idea of Go routine color is different than a Go routine name, we already have it already in a sense because a certain function runs. That's the kind of Go routine we're talking about. So in a sense, we have colors already, we just didn't know it. Now somebody might say, oh, wait a second, if you have Go routine colors, then you're going to get IDs. Or you could get IDs because you could give every Go routine a different color, and then they all have names. Yeah, okay. It opens that possibility, but it's not interesting that possibility probably, because there probably isn't an interesting program in which you color all the Go routines different colors. That's not probably very interesting. So we're really talking about something different here than IDs for Go routines. Let's make the runtime better. Yes, of course. We should make the runtime better, but not just make the runtime better. We can do other things too. And so here are the takeaways, the main takeaways from the talk. First, controlling the Go runtime is a good thing. I tried to explain why. I proposed some ideas for how we could do it in better ways, Go affinity, Go next get, and Go cancel. And I think in the background is really the thought, it's a good moment, I think, to be a bit more systematic about how we're thinking about the runtime, how we're making it do what we want, thinking about our algorithms, thinking about what sort of hooks we might need to have our programs run better. So with that, I'd like to say thank you very much for coming. I'd be happy to talk with anybody, see your programs in the next few days. Enjoy the rest of the conference.